Hello everybody, welcome back to lecture. So today's date is April 21st. Okay, and so we'll be talking about section 4.2, which is called log logarithmic functions. So the first thing we need to do is state exactly what a logarithmic function is. So we just learned about exponential functions. Right? And those were f of x equals a to the x, where a was positive and a wasn't equal to 1. Because a being equal to 1, 1 to any number is still just 1. So that's why we get rid of this case. And then a positive, because if we have a positive number here, then we don't have to worry about the even or oddness of the exponent. Okay, so this is what we learned about in 4.1. Okay, so we've talked a little bit about inverse functions, maybe not directly this year or this semester, but let's just have a brief reminder here, or review. Okay, so for example, whenever we solve equations, so if you can have a function y equals x plus 7. If I wanted to find the inverse, then you switch y and x. So in this case, it's very simple. It's just x equals y plus 7, and solve for y. So then if I subtract 7 from both sides and switch around the equality here, it's y equals x minus 7. So the inverse function of this function here is this one. So you could also write f of x equals x plus 7, and then this notation, f inverse, and then the x is equal to x minus 7. Okay, so that's for like addition and subtraction, but what if you had, so notice that it's also just subtracting, so if I wanted to get rid of the 7, I would just have to subtract 7 from both sides, which is eventually that's the inverse function. Okay, what if I had a multiplication? So like f of x is equal to 4x, and I wanted to find out what the inverse was. Well, I could write it as y equals 4x, and then you switch x and y. So now it's x equals 4y, and solve for y. So now y equals 1/4 x. So that's the inverse, right? If you want to get rid of the 4, you divide by 4. So back to our exponential function. What happens when you have this? And I wanted to find the inverse. So if I want to find the inverse, I replace the f of x with y. Get y equals a to the x. Okay, so how do I get this x by itself? Well, there's really no, we haven't defined, that's what this section is going to be about, is finding 4.2 logarithm function is inverse of the okay. So we've talked about the exponential function, so now we're going to talk about the logarithm function. Its inverse. Okay, so the way we define it here is for x greater than 0, a greater than 0. So notice this is a domain, right? This is saying that x is in 0 to infinity. It has to be a positive number. A greater than 0 and a not equal to 1. Alright, so then it says y equals log, and then we call this the base number a, x, if and only if x equals a to the y. Right, so it's if you have a function y equals log base a of x, you really are asking yourself a to the what number is equal to x. A to the what number is equal to y. I'm sorry, a to the y is equal to x. A to the y is equal to x. That's what you're really asking yourself here. Okay? So again, this is the base a. Alright, so you can put any positive number you want in this base. So let's talk about, so why would you want to not have a equal to 1? Well, so if I have 1 to the y is equal to x, well, that's not interesting because 1 to any power is equal to 1. Okay, so there's no point in having a equal to 1 because it's an uninteresting relationship. Okay, so a has to be positive here because if you take it's because that's the way we defined an exponential function. We want to talk about positive a's only. And x being greater to 0 is because if you're taking a positive number to an exponential function, right? Remember we learned that the exponential function can only be positive. Right? It always goes above 0. This exponential function at least, with no vertical shift. So that's why we have to insert positive x values. Okay, so we're going to call y equal log base a of x logarithmic form. And we're going to call x equal a to the y exponential form. Right, so it makes sense to get from here to here. So if I start with x equals a to the y, if I take the log of both sides, log base a of x, right? So you also have to think this is a function. Log base a of x is a function. Then if I take the log base a of a to the y, this is just going to equal y because log base a and a to the y, these two are inverse functions. Okay, so the log base a cancels out it brings the exponent down, essentially. So we're going to talk about a few examples first. So we have write each equation in logarithmic form. Okay, so there's exponential form and there's logarithmic form. So a is going to be 4 cubed equals 64. Okay, so they've given us 3 different equations in exponential form and are asking us to write it in logarithmic form. So for a, you see that looking at it's in exponential form, so x in question A, this is confusing because there's an a in here as well. In part A to the y, so a would be 4 and y would be 3. So we would say 3 is equal to log base 4 of 64. Right, this is saying 4 to the third power is 64. 4 to the third power is 64. Okay. Alright, so part B, this is going to be 1/16. Whoops, sorry. So 4 is going to be log base 1/2 of 1/16. It's saying 1/2 to the 4th power is 1/16, and that's also correct. And then finally C, we put into logarithmic form, and we get -2 is equal to base A of 7. Whoops. Yep, that's correct. Right, because here we have A is A, Y is -2, so -2 goes over here, and X was 7. So that's how you would set that one up. Okay, so that's how you change from exponential form to logarithmic form. So now we're going to go ahead and do the opposite. So write each equation in exponential form. So log base 3 of 245 equals 5. Okay, so for part A, we can look back at our logarithmic form here. So this is saying log base, so A would be 3, X would be 245. So this is saying 245 equals 3 to the 5th power. So 3 times 3 is 9. 9 times 3 is 27. Oh, this should be a 3. Sorry. Okay, sorry about that. So 3 times 3 is 9. 9 times 3 is 27. 27 times 3 is 81. And 81 times 3 is 243. Okay, so that's 3 to the 5th. All right, B is... Okay, right. So B is now... So if we look at our equation here, x is in the y spot, so it's 2 to the x is equal to 5. Right. Which we don't really know. Like 2 to the first power is 2, 2 to the second power is 4, 2 to the third power is 8. So how would you get that equal to 5? Okay, so then C is going to be a to the x equals n. All right, so that's, you just basically have to use these two formulas to convert back and forth. All right, so moving on. So that's how you convert from exponential to logarithmic, and they both mean the same thing. Okay, so now let's do a couple more examples. So this one's just about finding the value So the first one is A is log base 5 of 25. So how do we figure that out what that is? Well, we could convert it to exponential form. So this is really saying, so let's just put log base 5 of 25 equals our unknown number x. Okay, and then we will convert this to, or we can even say y, just to make this a little easier to use the formula. Okay, so now if we want to convert this to exponential form, because sometimes thinking about it in exponential form is the better way to think about this. Maybe I can flip this back. There we go. So if we look at our exponential form here, this is really, so it's going to be 5 to the y power is equal to 25. So 5 to the, this log base 5, 25 equals y is saying 5 to the what power is equal to 25. So we know that 5 squared is equal to 25, so y is equal to 2. Okay, so how about this next example? B. Log base 2 of 16 equals what? So you can start skipping the step where you put it into exponential form. So this is really saying 2 to the y power is equal to 16. 2 to the y power is equal to 16. So we know that 2 squared is 4, 2 cubed is 8, 2 to the 4th is 16. Alright, so C, this one's log of 1/3 equals 9, or log base 1/3 of 9 is equal to what? So this is saying 1/3 to the y power is equal to 9. So this is a bit tricky. So I could also rewrite this as this one, so it's 1/3 to the y power. So I could write this as 3 to the negative 1 to the y power equals 9. Or 3 to the negative y equals 9. So if I pick y to be any positive number, I'm going to get a fraction back, because it'd be y to a negative number overall. So I need to pick y to be a negative number so I can cancel out this negative. And if I pick y equal to negative 2, we get 3 to the negative 2 is equal to 3 squared. which is equal to 9. So y is equal to negative 2. Okay. All right, a couple more of these. So what about log base 7 of 7? So this is a good example because it illustrates that log base a of a is equal to 1, and we'll see why. So let's write this in logarithmic or exponential form. So it's 7 to the y is equal to 7. So y has to be 1. Okay. All right, and continuing on here, we have log base 6 of 1 equals. Sorry, gave away the answer. Gave away the answer here. Equals y. So now I put that in exponential form. So it's 6 to the y power equals 1. Well, any number to the 0 power is equal to 1. So y must equal 0. Okay. So that is a good one for illustrating that any logarithm with any base of 1 is equal to 0. So we have, last but not least, log base 4 of 1/2 equals what? So this is the same as 4 to the y power equals 1/2. So if I think about this, if I put in negative 1, if I put in a negative 1, I get, if I put y equal negative 1, it's 4 to the negative 1 power. So that's equal to 1 over 4. So we're close, but we want a 1/2. So if I did y equals positive 1/2, I'd get 4 to the 1/2, which is equal to the square root of 4, which is equal to 2. So close. So now I just need to take, but not correct. So if I did y equals negative 1/2, then it's 4 to the negative 1/2, which is equal to 1 over the square root of 4, which is equal to 1/2. So y would be equal to 1/2 for this example here. Okay. Alright, so continuing on. So we just saw from those two examples these two following properties of any logarithm function. So if a is greater than 0 and a is not equal to 1, then since a to the first power equals a, then log base a of a is equal to 1. So that's just taking exponential definition and rewriting it as a logarithm definition. And since a to the 0 power equals 1, a to the 0 power equals 1, then log base a of 1 is always equal to 0. So log with a base of any positive number and you input 1, well, besides 1, you get 0 back. And even if you did a equal to 1, this one would work as well. And so this one. All right. Oh wait, never mind. Just kidding. So yeah, just keep in mind with a not equal to 1. All right. So we've gone over those two properties, and we're going to add in two more. So we also saw that log base a of a to the x. So we can see this. What's log base a of a to the x? Well, written in exponential form, this is, if we put a y here, then this is saying a to the y equals a to to the x in exponential form. So in the exponential function, a, when a is positive and a is not equal to 1, is a 1-to-1 function. So that means that 1-to-1 function. So x equals y. So all in all, if x equals y, then log base a of a to the x is equal to x. And it makes sense because these two, log base a of its input and a to the x are inverse functions. If you want to bring the exponent down in front, you have to multiply it by the inverse. Or not multiply by the inverse, but take the inverse of it. Okay? So that's a third proposition, or a third property there, and then this one is the exact opposite. So a to the log base a of x is equal to x. So 3, 4. Okay. So let me just rewrite those for you. So we have log base a of a is equal to 1. And that's a special property of number 3 here, because if x were equal to 1, then 1 goes here and here. Okay. 2, log base a of 1 is equal to 0. 3, log a x equals x. And 4, a to the log a x is equal to x. Okay, so let's use these properties in some example problems. So the first example is they just want you to evaluate the following: log base 3 of 3. So log base 3 of 3 is going to be equal to 1 because of this property right here. We have the same base as its input. Okay, and the second one is 5 log 5 of 7. What is that equal to? Well, that's this rule here. The number in the base of the logarithm and the number, the non-exponent number, this 5 here, are the same. A and A are the same here, so this is going to equal 7. Okay, so now we're going to talk about the domains of logarithmic functions. So we talked about how the exponential function, a to the x, has domain negative infinity to infinity. You can plug in any x, and it has its range, however. If you have a positive number a to a variable x, you will never be able to get a negative number. So its range is actually only positive numbers. Right, so now if we're taking the inverse, then right, the inverse function is y equals log base a of x. So its domain is going to be this one's range, 0 to infinity. And its range is going to be negative infinity to infinity. Okay, so that's just saying whatever you put inside of the logarithm has to be a positive number. So let's do a couple examples of finding the domains of a logarithm function. So find the domain. So we have f of x equals log base 3 of 2 minus x. So we're taking the logarithm. It's asking us 3 to the what power equals 2 minus x, and it wants us to find the x, or this is the function. Okay, it doesn't want us. We have two unknowns, so we can't find anything. But this is just, if you plugged in an x, it would spit back out a y. All right, so we need, like I was saying before, we need whatever's inside these parentheses to be positive. So 2 minus x has to be greater than 0, because the domain of the logarithm function, when just x is inserted, is 0 to infinity. Okay, so now we solve this. So if I add x to both sides, you get 2 is greater than x. 2 is greater than x. Or you can write this as x must be in open bracket 2 to infinity. So the domain of this log base 3 of 2 minus x is 2 to infinity. All right. What about g of x equal to log base 2 of x plus 1 over x minus 3. Okay, so again, we need whatever's inside here needs to be positive. So x plus 1 over x minus 3 has to be greater than 0. So we can use the test point method to find correct interval. Okay, so we need to figure out the zeros of the numerator and the denominator. So 0, there's only going to be 1 for each since they're both linear. So 0 of numerator, num for short, is, you set x plus 1 equal to 0, so x is equal to minus 1. And for the 0 of the denominator, you go ahead and you set x minus 3 equal to 0, so x is equal to 3. X is equal to 3. All right, so now we have our intervals we need to check. We have the interval negative infinity to negative 1, negative 1 to 3, and 3 to infinity. So we have to pick test values in each one of these intervals here. So this one I'm going to pick negative 2, test values, 0, and 4. So if I plug in negative 2 to this inequality, I get negative 2 plus 1 over negative 2 minus 3, which is equal to negative 1 over negative 5, which is positive 1/5. And that is greater than 0. If I plug in 0, you get 0 plus 1 over 0 minus 3. That is equal to 1 over negative 3, which is not, put a little line through it, not greater than 0. Or here, duh, which is less than 0. All right, and then 4, finally if I plug in 4, 4 plus 1 over 4 minus 3 is equal to 5 over 1, which definitely is greater than 0. So this one doesn't work and this one works. So when I plugged in 4, it worked. When I plugged in 0, it didn't work. And when I plugged in -2, it worked. So the domain is the combination of these two. So the domain is -infinity to -1 or 3 to infinity. So that's how you find the domains of logarithmic functions. So just like whatever goes inside of a square root needs to be 0 or greater, whatever goes inside of a logarithm actually needs to just be greater than 0, strictly greater than. So let's do a kind of interesting one. Last example on domains. So f of x equals log base 10 of the square root of 1 minus x. So we've got both a square root and a logarithm here. Okay, so whatever goes inside the logarithm has to be greater than 0. So the square root of 1 minus x must be strictly greater than 0. Okay, so I also know that I cannot plug in numbers that are negative into the square root. So this must be true, and 1 minus x must be greater than or equal to 0. So let's solve this one first. So this is just adding x to both sides. So 1 is greater than or equal to x. Okay, so if you have that, then whatever you put inside the square root will be 0 or greater. So now if I solve this one, I would square both sides. So it's 1 minus x is greater than 0, because 0 squared is 0. All right, so now if I add x to both sides, you get 1 is strictly greater than x. So at the same time, you need 1 being strictly greater than x and 1 being greater than or equal to x. So the combined domain, if they both have to be true, then it's just this one. So it's just 1 to infinity. Oh, I'm sorry. I wrote this incorrectly. It shouldn't be 1 to infinity, right? Because 1 has to be greater than x, or x is less than 1. So it should be -infinity to 1. Alrighty. So we've talked about evaluating logarithm functions. We talked about finding their domains. So now the next thing we should talk about is graphing them. Graphing graphing logarithmic functions. Okay, so let's just graph y equals log base 3 of y. Let's do it with our usual method of just plotting points. To graph. Alright, so I'm going to make a table here. Sorry, this should be x. So we have x inputs over here and y outputs. So if I do x, so I'm going to choose this. You'll see why here. I'm going to choose powers of 3 in this as x. So I'm going to do 1 over 27, which is equal to 3 to the -3. That's going to be my first my first x input. Okay, and the second one is going to be 1 over 9, which is equal to 3 to the negative 2. And then I'm going to do 1 over 3, which is 3 to the negative 1. And then I'm going to insert 3 to the 0, so 1. And then 3. And then 9. And then 27. Okay, so if I do that, then y is equal to log base 3 of x. So negative 3, log base 3, 3. Well, sorry, that was really messy. Log base 3 of 3 to the negative 3. Okay, so I'm going to use the rule where, hold this back here. The reason I wrote it in powers of 3 was now I can conveniently use this rule here. The third one, log base a of a to the x is equal to x. So I have log base 3 of 3 to the negative 3 is negative 3. So here I can just keep going down the list. So log, for the same reason, and I'm inputting, notice I'm staying within the domain because 1 over 3 to the negative 3 is 1 over 27. It's still a positive number and it's not quite 0. It's just getting smaller and smaller to 0. So I've only inputted positive numbers here. So log base 3 of 3 to the 0, or 1, is equal to 0. Oh. There you go. Log. All right, and all right, so here I've got my points. I've got the x coordinate 1 over 27 and negative 3, 1 over 9 and negative 2, 1 over 3 and negative 1, and so on and so forth. So I'm going to plot this now. Okay, so if I plot this, I need kind of a big, a large, I need to go all the way out to 3 to the third power, which is 27. So I'm going to probably increase the x. So if this is the x and this is y, then I'll probably do like 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28. So I'm just going to mark some of these. 28, 20, 10, right. Okay, so I need to go all the way up to 3, 1, 2, 3, negative 1, negative 2, and negative 3. All right, so if I draw this graph, then if I get really, so my first coordinate pair is 1 over 27 on the x, so really close to 0, 1 over 27, maybe right there, and then negative 3, so it starts off like right there. Then I get 1/9, which is maybe a little further, and that goes to negative 2. Then I get 1/3, which is probably like a little bit less than half, so that's right there. Then as I insert 1, so if I insert x equals 1, which is about halfway there, I get a 1. So these dots should be even close together. Okay, so that's these first 4. And now if I insert a 3, which is this one, I should get a 1 back. And now if I insert a 9, which is all the way up here, I should get a 2 back. Now if I insert a 3, or I'm sorry, if I insert 27, I should get a 3 back. Okay, so now I'm going to connect these dots. And that's exactly what the logarithm function looks like. So it continues to go down. So it increases as it goes to infinity, and as it goes to 0 from the right, it goes all the way down to negative infinity. So that's why its range, right, its range contains the whole y-axis. Okay, but you cannot put negative numbers in the logarithm function, so that's why it only includes the positive x-axis. All right, so there's another method for graphing these this particular function. This one was f of x equals log base 3 x, right? Yeah. So another way is to first consider the graph consider its inverse. So the inverse of that is 3 to the x power. So we figured out how to graph this last section in 4.1. So 3 to the x power, if I put in negative 1, I get 3 to the negative 1, which is 1/3. So about right there. So if I put in 0, 3 to the 0 power is 1, so right there. And if I put in 1, you get a 3 back. If I put in 2, you get a 9 back. So it comes up like that. So this is f inverse of x equals 3 to the x power. So if I'm, for example, this point, right, I graph this point, or I put in x equals 1 and you get 3 back. So it's inverse, and this one was 0, 1, and this one was negative 1, 1/3. So the inverse of this function is if I just switch these two x and y coordinates. So now if I switch the x and the y coordinate, that means I need to graph 1/3, so about right here, and negative 1. So right there. This is the point. I don't want to write it there. So if I switch these, that's the point 1, 0. And then if I switch these, I get the point 3, 1. So, right, and you could keep doing this and connect all these dots. Goes on forever like that. So you can see how they're flipped, they're inverses. Okay. So yeah, they're flipped around. They have an oblique symmetry. So that's the other way you can graph it. If you graph the inverse function, then flip all the x and y coordinates. You can graph any function like that, actually, but it's particularly easy with this one. Okay, so that's how you would do the graphing. So just like all those shifts with the exponential graphs, you can have shifts and transformations of logarithmic graphs. So the vertical shift. So this is an abbreviated version of table 4.7 on page 450. So a vertical shift is y. So if you have the graph of log base A log base a of x. Then you want to vertically shift it up or down. It's y equals log base a of x plus c. So this changes it. So I'll make it 2 columns here. Xy 4 equals log. So this is so if xy are on this graph, then graph of y equals log base a of x, then y equals log base a of x plus c is going to give you x plus c, I'm sorry, y plus c y plus c. And this is all for c being a positive number. So this one would shift, if c were positive, oh no, this is for c, so far it can be anything. So if c were positive, it's going to move your graph up, and if c is negative, it moves your graph down. So the horizontal shift so this is y equals log base a of x minus c. So this one's going to be x plus c, comma y for any c. So if you put a positive number here, it'll shift it to the right. If you put a negative number here, it's going to shift it to the left. Okay. So then a reflection. So this is going to be y equals negative log a of x, and y equals log base a of x. So this one's for a reflection about the x-axis. This one's the y-axis. So sorry, I should box these together. I don't know why I drew a line there, but this one is going to be x comma negative y, and this one's going to be negative x comma y. And then vertical stretching. Slash compress. So it's y equals c log x, and this is going to give you x comma cy, and horizontal stretch slash compressing is y equals, so log a of bx, and this is going to give you x over b y. So it's the same table. It's essentially the same as the exponential table that we talked about last lesson. Okay, so I'll just do one or two examples of vertically stretching or compressing a graph here. So if you had f of x equal to, let's try log base 3 of x minus 1, Well, that moves the graph of log base 3. So moves graph of log base 3 of x 1 unit to right. Now instead of having our vertical asymptote at 0, we're going to have, so remember it was 1 over 27 and then mapped to negative 3, so now it's going to be 1 and 1/27 going to be mapped to negative 3. So 28 over 27. Because we're adding 1 to all the x values. Okay, so then it's going to be 1 plus, so 10 ninths, comma negative 2, and it's going to be 4/3. So if this is 2. And then it's going to be 4/3, comma negative 1. It's like right there, 4/3. Okay, and then, so now if I put 2 in here, I should get a 0 back. If I put a 3 in here, if I put a 4, it's going to be log base 3 of 4 minus 1, so that should give me 1 back. So it's just the log base 3 of x graph shift to the right by 1, because c is 1. Okay, so that's how you do a horizontal shift. I'm not going to go through all the explanations like I did last time with the exponential, but if you did, let's do one where you have a combined shift. So you have like a reflection and a horizontal shift. So this is a reflection about the y-axis. So we're going to get, so comparing it to y equals log base 3 of x, this is x and y, then excuse me one second. So then we're going to have a horizontal, so we'd get, it's going to be, you take your x coordinate and you make it x plus 1. And then since we have this negative out in front, that results in a negative y coordinate. So that's the reflection. Right, because on the table, the reflection about the x-axis gives us a negative here, so we make it a negative y, and then we're going to move it plus c over, which c is, I should maybe make this, there we go. Whoops, nope. X plus c. I did make it. So, and then we're going to shift it c over for the vertical shift, because we have negative log base 3 of x minus 1. Okay, so if I draw this, we're going to get this graph, but just flipped over upside down. So this is going to be 1, 2, 3, 4, 4, 3, 2, 1. And then we want a negative 1 1, 2, 3. So if we're flipping, right, we already added 1. In this graph, this is log base 3 of x minus 1. So now we just need to flip it over. So if we're going to flip it over, make all the y coordinates negative. So then instead of 28 over 27 and negative 3, we're going to have 28 over 27 and positive 3. And then 9, 10 over 9 and positive 2, and then 4 over 3 and 1. So I flipped all the exponents there, and then or all the y coordinates there, and then making 0 negative is the same thing. So this is 2 comma 0. And then now we've got, if we insert 4, here we had 4 positive 1, now we need 4 negative 1. Now we can connect these. There. So that's how you would get a combination. So this one has a reflection of the graph y equals x log 3 across the x-axis, and it also moves it over 1 to the right. Okay. So I want you to notice that in this final graph, the logarithmic function has the log base 3 function. Let's get a graph of that one out, actually. We have 2 of them somewhere. Yeah, okay, so the log base 3 function of x has a vertical asymptote at x equals 0. So just like if I remember when I shifted vertically the exponential, so yesterday when I shifted the vertical, if I did a vertical shift on the exponential function, I changed that exponential function horizontal asymptote by that vertical shift. So the same idea is here. Since originally with no horizontal shift, I have a vertical asymptote at x equals 0. If I horizontally shift that to the right, then I have a new, by 1 unit, I have a new vertical asymptote at x equals 1. So in general, the logarithmic function y equals log base a of x minus c has a b vertical asymptote at x equals c. So if c is 0, then it has a vertical asymptote at x equals 0. So now, using that piece of information, they want you to give domain, range, and vertical asymptote of f of x equal 2 plus 2 plus log base 2 of x minus 1. Okay, so starting with the domain, we used to only have 2 things to look out for. We used to have dividing by 0, and the square roots have to have square roots of even power have to have non-negative numbers in their inside of them. But then if now we have another thing to look out for. If we have a logarithm, whatever's inside the logarithm must be positive. So there's no divisions, there's no roots, so x minus 1 has to be strictly greater than 0. Okay, so this is solved by just adding 1 to both sides. X is greater than 1, so then the domain is 1 to infinity, open bracket, because we don't include 1. Okay, so then the range is still going to be negative infinity to infinity, because the range of log base a of x. So this is just any number a, not even 2. 2 could be in a, but any positive number a, since the range of is negative infinity to infinity. So just because we're shifting log base 2 of x minus 1 up or down, it's still going to graph, right? So if you think of this graph, it's just the log base 2 function, which looks kind of like this. And it's just shifting it over to the right 1 unit and up 2 units. So it now looks like this. So 1, 2, 1. So you have a new vertical asymptote there, but then you're still gonna, the range it's still gonna go off to positive. It's gonna increase the bigger number you put in for x, and it's gonna go all the way down to negative infinity, no matter what the number that you put closer and closer to x equals 1. So the range is still negative infinity to infinity. Okay, and then for finally, if you want to find the vertical asymptote, well, we have to look for what c is. So c is just going to be c equals positive 1. So there's a vertical asymptote at x equals 1 by this rule here. Okay, so that was that example. So now we're going to move on to some common bases that people work with. So some common number a's. So one is called a common logarithm. Okay. So this one is, so if you just write log of x, then people just assume that you're talking about base 10. So if you write a log without a base, that just assumes that you're talking about log base 10. So this is y in exponential and logarithm form here. Y equals log base x if and only if x equals 10 to the y. Okay, and then there's the natural logarithm. So this one is that Euler's number e, which was like 2.71 dot 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 dot. So this e is the base. And then people use a different one. They say y equals natural log. So little l, little n, x. So they're really talking about log base e of x, but they just abbreviate it like this. So this one is y equals natural log of x if and only if then x is equal to e to the y. Okay, so they're just special cases of what we've been talking about so far, just special bases. So, I also want to show you guys that sometimes when we're evaluating certain logs, it's hard for us to do it because let's say I asked you to evaluate log base. So this goes back to what we were doing at the beginning. So log base 3 of 5. So this is really asking me if I set this log base 3 of 5 equals y. I want to figure out what y is. So then this is saying 3 to the y is equal to 5. Well, 3 to the y, 3 to the first power is equal to 1. 3 to the second power is equal to 9. So it's somewhere in between 1 and 2. But this is the ones where you're going to have to use a calculator. Okay, because those are too hard to figure out on your own. All right. So last but not least, I'd like to talk about an application. So we talked a little bit last time about a continuous and compound interest. Continuously compounded. Okay, and we had a formula for that. So we had A, the amount after T years in a amount of money after T years in a bank was its principal investment times E, the number E, Euler's number, times the rate, annual rate of interest rate, times time. A equals PE to the RT, rate. Okay, so this is going to be in exponential form. So now if we wanted, since we've learned about logarithms, we might as well see what the logarithmic form is. So if I take the natural log, the natural log of both sides. So then the natural log of A has to be equal. If these two numbers are equal, then the natural logs of them are equal. Natural log of A is equal to the natural log of PE to the RT. I'm sorry, that's not the first step I want to do. We will take the natural log of both sides at some point. But the idea is we want to get the exponent. We don't want to have an exponent anymore, and we want to use the natural log because that's the base we're working with. So I eventually want to use this rule. Log base A of A to the x is equal to x. Okay, except I'm going to use it with the natural log. So it's going to be A, first going to divide P from both sides. So A over P is equal to E to the RT. Right? That's legal. As long as you haven't invested $0, we can divide by P. So now to bring this exponent down, I'm going to take the natural log of A over P, right? The logarithm is the inverse of the exponential function. So now I'm going to use this rule because this is, remember, natural log is the logarithm base E of E to the RT. So it's log base E of E to the RT is equal to the RT. So this is now natural log of A over P is equal to R times T. And this is logarithmic form. Okay, so we have exponential form of continuously compounded interest, and we have a logarithmic form here of continuously compounded interest. So someone might ask you, this is useful because someone might ask you, so how long to double my principal investment at R equals 6.5% compounded continuously. Okay, so for this one, I need to figure out the time. How long is it going to take me to double my p? How long is it going to take for a to be 2 times p? So that's the first step. So doubling my principal means that a is equal to 2 times p. So I'm going to use the logarithmic form. So it's going to be the natural log of 2p over p is equal to 0.065, the rate, times time. That's what I want to solve for. I want to see how long it takes to double my investment. So these p's cancel to a 1, so you get natural log of 2 is equal to 0.065 t. Okay, and then to solve for t, the natural log of 2 is a number, so I divide by 0.65, divide by 0.065, and t is then equal to the natural log of 2, which you can put in your calculator, over 0.65. Okay, and that's about 10 2/3 years. So use a calculator for that one. Okay, so they also might ask, at what interest rate would it take to double my principal in 5 years? So again, for this one, I will use the logarithmic form. So it's natural log. I still want to double my principal, so a is going to be 2 times p over p is equal to, now this time they give me a time and they want to see what kind of rate they would need. So r is going to be what we're solving for times 5 years. So this is natural log of 2 again equals 5r. So then we want to solve for r, we divide by 5 on both sides and you get natural log of 2 over 5 is equal to r. So this r is equal to, using a calculator again, because you need to use the calculator for natural log of 2, that's about 0.1386. So, or in other words, 13.86%, which is a pretty high interest rate. But that's what it would take to double your money compounded continuously for in 5 years. You need a rate like that. Okay, so I'm out of time, and that's what I'm going to leave it at today.